The last part of this lesson will cover the final rule of our probability calculus. But first we're going to use the famous Monty Hall problem to illustrate the need for this rule. So there are two aims for this lesson. First, figure out how to solve the Monty Hall problem using an informal characterization of the law of total probability. And then we'll look at how to formally define that law, as well as how to use it in an example. The Weisberg text we've been using introduces probability with the discussion of the so-called Monty Hall problem, and it gives an intuitive feel for the conclusion. But now we've got the rules of the probability calculus at our disposal, so we can actually give a gloss of the mathematical solution to the puzzle. So first, here's how the puzzle goes. You're on the TV game show Let's Make a Deal. The host, Monty Hall at the time this problem became famous, he invites you to play the following game. In front of you are 3 doors, all closed. You are told that 2 of them have a goat behind them, and behind one is a new car. The car is equally likely to be behind any of the 3 doors. You are asked to choose one of the doors. Once you do, Monty Hall opens one of the 2 remaining doors. He will always open a door to reveal a goat. Once he does that, you're permitted to switch the door you chose. So based on Monty Hall's behavior, should you switch your choice? The answer is yes. Why? Let's first give a very general statement of the answer. Monty Hall reveals new information to you. He opens a door to show you a goat, and he can only open a door that shows a goat. He can't show you the car. Which door he opens, then, depends on which door you initially choose. Chances are he couldn't open the other door, so there are 2 doors you didn't choose. Chances are he could only open one of them because the car was behind the other. So it's more likely that you'll find the car behind the door that Monty Hall didn't open, but that you didn't choose. How do we show this? We need to compare the probability that we'll win given that we switch to the probability that we win given that we don't switch. So we're going to now look at the reasoning that shows we're more likely to win by switching. We're going to show the reasoning for the Monty Hall problem in the situation where the car is behind door 1. So each of these circumstances shown at the top, you'll see the car is behind the far left door. The orange figure in these 3 diagrams represents the door you randomly choose. Door 1 in the first one, door 2 in the second, door 3 in the third. Since you randomly choose the door, and the 3 choices of the doors are mutually exclusive, right? You can only choose one door at a time. That means each of these circumstances is equally likely. So we assign each one of these choices the probability 1/3. Once you choose a door, Monty Hall can only open a door to reveal a goat. So the door he opens in each of these circumstances is marked with the green goat. Now what we have left to do is determine the probability of winning in each of these circumstances. First in the situation where we switch, and then in the situation where we don't switch. Since in each of these circumstances we're holding fixed where the car and the goats are, the chances of winning, given where you're standing, are either 0 or 1. So we're just saying you win if you switch in this one, or you don't win if you switch in this one. First, we're going to consider what's the probability that you win given that you switch doors. And we'll look at each of these circumstances in turn. So again, the 1/3 represents the chance that you choose that particular door. holding fixed what's behind it. Do you win or not if you switch doors? In the first circumstance, you stood in front of the car, so you lose if you switch doors. That gives us the probability of winning of 0. You can't win if you switch. But in the second and in the third circumstances, you originally stood in front of a goat, right? You're going to do that 2/3 of the time. Monty Hall could only show you a goat. So the car had to be behind the third door. Not the one that Monty Hall showed, not the one you were in front of, but the one you hadn't chosen yet. In that case, you win if you switch. So in circumstances 2 and 3, the middle and right ones, we write our probability of winning as 1. You're guaranteed to win if you switch in each of those circumstances. Adding all of those possibilities together, we get the chance of winning given that we switch as 2/3. Now let's look at what happens if you don't switch. In the first case, you stood in front of the right door. So you win, probability 1. But you had a 2/3 chance of standing in front of a goat initially. So in those two cases, you lost in the second and third ones. So the probability of winning in the middle and right-hand circumstances was 0. That gives the chance of winning if you don't switch as just 1/3. 2/3 is better than 1/3. That shows you're better off switching. Now here we've laid out the example with the car behind door 1, but the same logic applies regardless of which door the car is actually behind. And the rule that allows us to sum up the chance in each of these circumstances of winning given that we switch, or winning given that we don't switch, the ability to sum is determined by the law of total probability. And we're going to look at a formal definition of this rule now. The law of total probability is a rule that allows us to determine the chance of some sentence being true when we don't know it immediately. And we determine it from what we know about some other complex probabilities and the probabilities of other sentences. So let's specify exactly what that means. The rule is as follows. For any two sentences, P and Q, the probability of P being true can be given by the probability of P equals the sum of the probability of P and Q, that conjunction, plus the probability of the conjunction P and not Q. So the probability of P is given by the sum of the probabilities of two conjunctions. Now we have a rule for giving the probabilities of conjunctions. By substituting each of those conjunctions with the formula given by the general conjunction rule, we can write these as the probability of P given Q times the probability of Q, plus the probability of P given not Q times the probability of not Q. Again, to clarify the relation between these two versions of the formula, the first one asks us to use the probability of conjunctions. The second version just uses the general conjunction rule to tell us how we calculate the probability of each of those conjunctions. So the general conjunction rule just tells us what we can substitute to do the calculation. The probability of P and Q in the top formula, that first term, is rewritten in the second formula as the probability of P given Q times the probability of Q. And then back to the top formula. The probability in that one of P and not Q, that's rewritten in the bottom formula as the probability of P given not Q times the probability of not Q. How do we make some further sense of this rule? It turns out that despite the fact that the formula looks pretty complicated, the basic idea is relatively straightforward. First, either Q or not Q must be true. So Q and not Q are mutually exclusive and exhaustive possibilities. Our rule gives us a way of determining the chance that P is true. What is that chance? It's the proportion of circumstances that make P true on each of those exclusive and exhaustive possibilities. And then we weight the proportion of the times that P is Q by how likely Q and not Q are to be true. In terms of the diagram here, it's easiest to explain the law of total probability in terms of the conjunction version of the rule. What the rule tells us to do is add the two parts of the circle that show circumstances where P is true. So the first term is that sliver where P and Q are both true. And the second term is the larger chunk of P that doesn't overlap with Q. It's within the space of not Q. So that circle Q and the stuff outside of it, not Q, carve up the whole space. Part of the P circle is within the Q circle. That's the first term. Part of the P circle is within the not Q space. That's the second term. The reason the law of total probability works is that we're adding up the chances that P is true along with the mutually exclusive options Q and not Q. Remember that these properties tell us that Q and not Q can't both be true together, and that we'll always be in circumstances where one or the other of these options is true. Remember, that's the definition of a partition. It's a mutually exclusive and exhaustive set of sentences that carves up all the possibilities. So Q and not Q, they divide all the possibilities up into two categories. But partitions can divide up possibilities into any number of parts. So we have a diagram to the right here with a partition. And the partition is formed by A1, A2, A3, and A4. With the concept of a partition in hand, we can then actually give a general statement of our law of total probability. If we have a set of sentences that form a partition, if they're mutually exclusive and exhaustive of all the possibilities, we can give the probability of P as the sum of the probabilities of the conjunction of P and then each of the statements in the partition. So we've got P and A1, we want the probability of that, and so on and so forth for each of the sentences in the partition up to P and AN, where there could be n sentences that form the partition. So returning to our diagram, the probability of P in that oval there is given by the chance that P is true in each of those quadrants, A1, A2, A3, and A4. It's kind of like adding up the sizes of the pie pieces to get the size of the whole pie. Now let's look at how to use this rule with an example. Let's say that 3 out of 10,000 people have some disease X. And there's a test for disease X that gives false positives 1% of the time and false negatives 0.5% of the time. We want to know, what's the chance that a random individual tests positive for the disease? First, we want to know, as our end answer, what is the probability of T, the chance that an individual tests positive for disease X? One thing we're given is the probability of D, the chance that an individual has disease X. So the probability of D is 3 in 10,000 or 0.0003. The probability of T, of course, is not given to us directly in this problem. That's what we're going to try to solve. And we can do that using the law of total probability. So substituting in T and D as our sentences, we're going to have the probability that someone tests positive for disease X is the probability that they test positive and have the disease plus the probability that they test positive and don't have the disease. So the chances of T are the chances of T in each of those mutually exclusive and exhaustive possibilities. The version of the rule that we're going to use, though, because it's the one that's in general more useful, is the bottom version with conditional probabilities. That's because, as we'll see in a second, the problem doesn't give us the information that we need to get the conjunctions immediately, but it does give us the information we need to get the conditional probabilities T given D and T given not D. Because we already have the probability of D, and we can easily get the probability of not D. So let's figure out, how do we get these terms that we don't have yet? We have the probability of D so far. We have 3 more terms we need to get the numbers for. And this will give us our conditional probabilities. The first one we need is T given not D. That's the chance that we test positive given that we don't have the disease. That's what a false positive is. And the problem tells us the chance of a false positive is 0.01. So the probability of T given not D is 0.01. The other conditional probability we need is T given D. That's the chance we test positive given that we do have the disease. What might not be obvious is that the problem didn't tell us that directly, but it did tell us what we need to know to figure it out. It told us the probability of a false negative, the chance of testing negative given that we have the disease. A true positive, which is T given D, is 1 minus the chance of a false negative, which is 0.995 in this case, because there was a 0.5% chance of a false negative. So now we have the probability of T given D, the probability of D, and the probability of T given not D. The only number we haven't explicitly calculated yet is the probability of not D, that very last term. For that one, we use the rule for calculating the probability of a negation, because we have the negation of D. The probability of the negation of D, the chance that we don't have the disease, is 1 minus 0.0003. 1 minus the probability of D. So that's where that 0.9997 number comes from. So looking at that second line, 0.995 is the chance that someone tests positive given that they have the disease. We multiply that by the chance that we have the disease, 0.0003. That product gets added to the product of the chance that someone tests positive given that they don't have the disease times the chance that someone doesn't have the disease. So that's 0.01 times 0.9997. Our final answer is approximately 0.13, which tells us that a random person has just over a 1% chance of testing positive for this disease. And with that, we're done with lesson 9 and our coverage of the rules of the probability calculus. So after this lesson, you should know how to determine conditional probabilities, how to determine whether statements are independent or not, how to calculate the probabilities of any sentences involving conjunction, now that we have the general conjunction rule, how to use the law of total probability to determine the probability of a statement when you don't know it straight up, and you should know, at least generally, why it's better to switch in the Monty Hall problem.